material from which a cutting tool is made must, to be effective, possess certain properties. Red hardness, abrasion resistance, and toughness are essential. A cutting tool must of course be harder than the workpiece it's cutting, otherwise it won't cut. It must also remain hard even when operating in conditions of great heat. The ability of a cutting tool to retain its hardness at high temperatures is known as red hardness. This is an old-fashioned high-carbon steel cutting tool containing 1 to 1.4% carbon. As you can see, it burns out very quickly. Although high-carbon steel is very hard at room temperature, as soon as the temperature rises, the steel begins to anneal and the hardness is lost. This process, known as tempering, has all sorts of industrial uses, but in metal cutting it can be a bit of a nuisance. When you're using high-carbon steel, cutting speeds have to be kept relatively low. This was a severe handicap when high-carbon steel was in widespread use as a cutting tool for lathes like this one. Even the simplest cutting operation took an extremely long time. These days, high-carbon steel is mainly used to produce cheaper wood-cutting tools. High-speed steel was introduced earlier this century and is the most commonly used material for making cutting edges on machine tools. Although at room temperature it's not as hard as high-carbon steel, it retains its hardness and has excellent red hardness at cutting temperatures up to 600 degrees centigrade. High-speed steel derives its properties from alloying elements like tungsten, chromium, and vanadium. The most common ratio is 18 parts of tungsten, 4 parts of chromium, and 1 part of vanadium in 7% carbon steel. Because it's an expensive material, only the actual cutting end is made of high-speed steel. This is welded to a cheaper carbon steel shank. Flash butt welding is often used. First, the tool and the shank are precisely aligned. A high current is used to melt the adjoining faces, which are then thrust together, forming a perfect weld. The process sets up a great deal of unwanted stress in metal. This is removed by heating to 850 degrees centigrade, a process known as normalizing. Once cooled, the tools are ready for pre-shaping. This allows the appropriate geometry of the finished tool to be ground, while the metal is still relatively soft. Heat treatment is perhaps the most important stage in the production of high-speed steel tools. It's from heat treatment that the tools derive their cutting properties. The first stage is a preheat, in which the tools are raised to 850 degrees centigrade. After a few minutes, they're removed and placed in the main chamber at 1200 degrees centigrade for a further period. They're finally quenched in a stream of hot air. Once cleaned, there's one last grinding which imparts a good cutting edge. The cutting edge can be reground again and again until high-speed steel is completely worn away and the toughened shank is reached. At this point, the tool is scrapped. The same principles are used in other cutting tools, such as high-speed twist drills. As in the lathe tool, only the cutting end is made of high-speed steel. In this particular example, the cutting end is friction welded onto the toughened shank. On larger twist drills, the fluting is milled onto the high-speed steel before heat treatment, which of course would make the metal harder and more difficult to machine. After milling, the drills are heat-treated in several stages. An automated carousel ensures that the drills remain in the liquid salt baths for the right period of time. Smaller twist drills made entirely from high-speed steel, and because of their size, are heat-treated before the fluting is ground out of the metal. The finished twist drills are used with a wide range of metals, and they give a high rate of metal removal. They have the same cutting properties as high-speed steel lathe tools. The lathe tools are ideal for drilling work, and also more than adequate for heavy-duty cutting. The drawback with these welded cutting tools is that when the cutting end has to be reground, the tool must be reset before cutting can start again. One way to overcome this is to use high-speed steel inserts. These are produced by a method known as powder metallurgy. Carefully measured powdered high-speed steel is put in a press. A die then compresses it into the desired shape. At this stage, the insert is known as a biscuit, and it's very brittle or friable. The inserts are baked in an oven at a very high temperature in a carefully controlled atmosphere. This causes the particles of high-speed steel to shrink and bond together, making the insert extremely hard. The inserts are produced in a wide range of shapes and sizes. After checking the final geometry, the insert undergoes facial and peripheral grinding. Although the inserts can be used at this stage, most undergo a coating process. Placed for about 9 hours in a vacuum chamber at temperatures exceeding 1,000 degrees centigrade. During this period, a very thin coat of titanium nitride or carbide, about 6 or 7 microns, is added to the surface. This coating improves the cutting properties of the material and extends the life of the tool. The range of inserts produced suits most cutting operations. Their great advantage over traditional high-speed steel tools is that when a new cutting edge is needed, you simply change the insert and there's no need to reset the tool. For machining hard and brittle metals like cast iron and cast bronzes, which have a highly abrasive skin and produce short chips, a specialized cutting material is needed. The carbides of certain metals, notably tungsten, are extremely hard, but not tough enough to stand up to the rigors of the metal cutting process. In the 1930s, it was found that these carbides could be bonded together by another material, cobalt. The result was a cemented carbide. In the beginning, because of the expense of the process, the cemented carbide tips were brazed onto the tool body. This only added to the cost, because when the tip wore down, it had to be reground painstakingly using a silicon carbide wheel. And after all that, the tool had to be reset. Nowadays, to save time and money, specially prepared inserts and holders are used. Holders made from toughened steel, which first undergoes a series of milling operations. To ensure a high rate of production and accuracy, CNC drilling equipment is used to form a clamping section into which the insert will be placed. Accuracy is essential. When the insert is changed, the positioning of the replacement must be identical so that cutting can continue without any need to reset the tool. The inserts are produced by powder metallurgy, similar to the process used with powdered high-speed steel. Tungsten carbide is milled to a fine powder and mixed in the desired quantities with powdered cobalt. This mixture is placed in a mold and pressed to form a slug. As the inserts are friable at this stage, they're handled with specially designed and very sensitive equipment. Cemented carbides normally contain 70 to 90% hard particles, together with 10 to 30% cobalt binding film. The more cobalt present, the tougher the cemented carbide. Unfortunately, increased toughness results in decreased hardness and resistance to abrasion. So the next stage is sintering in an oven at a temperature in the region of 1600 degrees centigrade. A cover gas of hydrogen prevents the oxygen in the air from damaging the insert. The result is a fully hardened insert. Then they go on to a variety of automated grinding processes. These ensure correct geometry of the inserts before coating. In principle, the coating is similar to the one applied to high-speed steel inserts. These days, many of the carbide inserts have a double coating. The titanium carbide layer gets an additional coating of aluminium oxide. This produces a durable cutting edge, which gives almost twice the metal removal rate you'd get from a single coating. The finished insert is then packed, and the boxes are given international color coding according to the grade of the insert. Those used for machining steel are colored blue and lettered P. These will cut steel with maximum efficiency as their structure provides high resistance to thermal cracking and plastic deformation. Inserts used for machining cast iron and non-ferrous metals such as cast brasses or those metals which form short chips are coded red and given the letter K. These are ideally used at relatively high cutting speeds with low feeds. Finally, those color-coded yellow and letter M. They're mainly used for machining exotic metals and alloys which are difficult to cut, such as titanium or aluminium. Here, titanium bar is being machined at the low cutting speed and high feed rate normally used with these inserts. Care should be taken to choose the right grade. That way you get better tool performance and better surface finish. To help guide the operator, each insert has a number. The higher the number, the tougher the tool. The lower the number, the harder the tool. Tungsten carbide inserts can be used for most machining jobs, and they're easily chained. They have several cutting edges. This triangular insert has 3 cutting edges on each side, a total of 6. Although inserts are easily changed, with the new CNC machines in use for high production batches, even these changeover times are considered slow. A new system is that of block tooling. The block tool has an insert already fitted and can be changed in a matter of seconds by simply slipping out the old tool and fitting in the new. The old insert can then be changed while the machine is cutting with the new tool, so a minimum amount of time is wasted. Tungsten carbide is also used for milling cutters on the same range of materials and using similar inserts. This particular example proves that the right insert has no difficulty dealing with an intermittent cut at high feed rates. When used for drilling, carbide sides, due to the composition, can't be placed centrally on the drill head. If they were, they wouldn't last long. This is easily overcome by offsetting the tips. Usually the drill head is hollow, allowing the swarf to pass up the center of the tool and be ejected behind the drilling equipment. Ceramic tips are even harder than those made from metallic carbides. They're also more brittle. Once again, powder metallurgy is used to produce the tips. They're pressed in a mold which is oversized to allow for the shrinkage which takes place during sintering. The ceramic material most commonly used is sintered aluminium oxide, either commercially pure or mixed with other metallic oxides like chromium. Sintering is carried out at 1600 degrees centigrade, and the tips have to be very slowly cooled to avoid cracking. Ceramic tools are used mainly for finishing cuts at high speeds and fine feed. Cutting speeds of up to 300 meters a minute are quite common. Under these conditions, ceramics can produce excellent results, but because of their brittleness, they are seldom used for intermittent cuts. This is due to the high forces involved, which can cause the tips to shatter. Although diamonds may be a girl's best friend, only 20% of diamonds mined are suitable for use as jewellery. The remaining 80% play an important role in industry. As the hardest material known to man, their industrial applications are constantly being widened. In this factory, most of Europe's industrial diamonds are processed. The rough diamonds from the mine are first graded in a vibrating stack of different sized sieves. After sizing, the diamonds are separated for color. A photocell senses the depth of color in each diamond and grades accordingly. An air jet shows the darker ones into a color box. These are unacceptable as gemstones, but ideal for use in industry as cutting tool material. When the appropriate stones have been selected, they're carefully mounted, making sure that they're properly aligned. Diamond tools are best used on vibration-free equipment, such as this lathe, which is specially designed to put the finishing cuts on aluminium computer memory disks. To give the discs the best surface finish possible, cutting speeds are very high. In this case, they are 4,000 revs per minute. Although hard, diamonds are also extremely brittle, and they can easily chip or fracture. The structure of the crystal is made up of millions of regularly spaced carbon atoms. Due to this regular shape, the stone has its strong points, but also its fracture planes. These weaknesses are used by jewelers when they come to cut the stones. It's shock to these weak fracture planes which causes the industrial diamonds to chip. This can pose problems in industry. What's needed is a diamond that doesn't chip. A polycrystalline or synthetic diamond differs from a natural diamond because instead of a single crystal, it's got thousands of randomly placed crystals joined together. It's because of this crystal orientation that the problems of cleavage and fracture don't arise. Even if one or two crystals are fractured, it wouldn't affect the overall performance of the tool. There are thousands remaining which are correctly aligned. Synthetic diamonds are made by simulating the conditions that once created natural diamonds. Years of research has gone into the development of equipment capable of producing pressures of 1,000,000 pounds per square inch and temperatures up to 2,000 degrees centigrade. The basic ingredients for the process are these discs of graphite, which are loaded into a capsule interspersed with discs of transition metal alloy. The exact nature of the alloy is a carefully guarded industrial secret. The capsule is placed in the center of high-pressure die in this hydraulic press. At the top and bottom, two horizontally opposed tungsten carbide anvils. At the back of this press, heavy braided copper leads give some idea of the enormous currents which pass through the anvils to generate the necessary temperature. When the right pressure and temperature conditions are reached, the metal melts and acts as a solvent, recrystallized in the form of a diamond. What emerges is a hard slug of metal with some diamonds dispersed in the middle. These slugs have to be processed in large vats of acid. The acid dissolves the metal alloy and leaves fine sand-like particles of diamond, which form the basis of the cutting tool. The basic structure is a laminate one with a dense layer of polycrystalline diamond bonded to a tungsten carbide base. The tips can be either clamped or, as in this case, brazed to the shank. The tungsten carbide layer is responsible for the toughness and resilience, particularly during shock loading, while the polycrystalline diamond layer gives better tool performance. Due to this random polycrystalline structure, the tools have uniform properties in all directions, and there are no problems of orientation. Each tool has identical properties. These tools can be used for a variety of cutting processes with non-ferrous metal, and they are particularly efficient for cutting aluminium alloys and castings such as pistons. These alloys, which contain highly abrasive silicon particles, a test for any material, are easily machined. A synthetic diamond tool, although initially expensive, can last up to 10 times as long as the tungsten carbide equivalent, and when used for intermittent cutting. Neither diamond nor polycrystalline diamond tool can be used to machine ferrous metals. This is due to a chemical reaction with the carbon which causes metal buildup. However, a new material, cubic boron nitride, or CBN, has been developed for use in these cases. It's the result of a great deal of research based on boron and nitrogen, both closely related to carbon in the periodic table, and using the same technology employed in making synthetic diamonds. CBN is the second hardest material known to man, and it's chemically inert at temperatures below 1000 degrees centigrade. Because it's so expensive, it's only being used at the moment for machining difficult materials, such as this very hard cast iron. But when production costs are lowered, it's bound to have a useful and exciting future.